So welcome to our next, actually our final session in the switching topics, which is our discussion about WAN circuits and specifically PPP. We're going to take a look at WAN circuits. You guys can hear me okay? Good to go? All right, let me know if you can't. Awesome. So we're going to take a look at WAN circuits today. It's a really basic topic, but you know, we could actually probably cover it in about 20 minutes, but I've decided to go ahead and kind of add quite a few things to this discussion because I do think it's important. Not so much Hdlc. There's not a whole lot you can do with Hdlc, but you're going to be tested on a lot of these concepts on the written exam as well. So I thought it was important that we would kind of go through a lot of these discussions about Hdlc and why Hdlc is still a widely used WAN circuit protocol. But so that's what we're going to focus on in this last switching lesson is what is a WAN circuit, specifically Hdlc and PPP. We're going to take a look at basic Hdlc configurations over a serial interface. But Hdlc as a protocol doesn't offer a whole lot of the other functions that, say, for example, PPP offers. PPP is actually a different type of transport protocol at layer 2. It does negotiation. It has authentication elements. We can run PPP over Ethernet, but we can't run Hdlc over Ethernet. And it has a bunch of other miscellaneous features that just don't simply exist inside of Hdlc. So before we start getting into the details, let me first talk to you about the scope of the circuits on the exam. Frame relay is obviously no longer going to be included, either on the written exam or the lab exam. You're going to see serial interfaces, but as far as the amount of topics that are covered on the scope of the exam, they're going to be really, really small. I mean, there's not going to be a lot of discussion about, or you're not going to see a lot of configuration. If we go look at, in fact, let me pull that up. If we go take a look at the blueprint, let me pull the blueprint up for you guys. Assuming my computer will cooperate with me today. I got the little blue screen of death when I opened my computer this morning, and I've been trying to recover ever since. So, all right, let's see here. Class shares, CCIE, and if I go into, seriously, come on. They're folders. How hard can that be? I wonder if I've somehow managed to fill up my hard drive. All right, so let's take a look at the blueprint. This is the written blueprint. I think we're going to be more concerned about the lab blueprint specific to layer 2 technologies. Let's take a look at what we've got for this particular section. Let's see, VLANs, PAGP, rapid spanning tree, LAN switching, multicast, WAN technologies. So in section 1.3, implementing and troubleshooting Hdlc, which is a really, really simple concept. Implementing and troubleshooting PPP, you need to be aware of both PAP and CHAP authentication. So we're going to talk about that today. Pppoe, point-to-point protocol over Ethernet, and multi-link PPP, which we probably won't take a look at today, but I'll instruct you guys on a document that you can read to learn more about multi-link PPP. I doubt you're going to see actual multi-link PPP on the exam. Our focus is primarily going to be on the basic authentication and setting up PPP over Ethernet. Okay? So that's what we're going to be looking at, and based on the blueprint, that's what we're gonna take a look at. All right, we're not really building a huge topology for this. We're just using a couple of routers back to back with a serial link. There aren't really too many applications of these protocols in the real world anymore because most of our technology is going to be higher speed, like Ethernet or other types of high-speed connections. So let's start by taking a look at Hdlc. Now, before I get into the actual configuration, I'd like to start to maybe get into a little bit of the protocol itself, and then we'll get into some more of the application stuff in a little bit. The configuration is really straightforward. So again, this is not something you necessarily would need to know for the lab exam, but it could still be pretty useful for the written exam. All right, let me pull up Notepad. And we'll start by talking about Hdlc, which stands for the high level, if I could type, Datalink Control Protocol, Hdlc. All right, now it is a bit-oriented protocol, which means it pretty much operates at the, well, it's transparent to the data link layer. It's still a data link, considered a data link layer protocol, but it is a bit-oriented protocol. So it synchronizes our data link protocol. It was developed originally by OSI, or ISO, excuse me. Developed by ISO, the International Organization for Standardization. There's a bunch of specifications. You're not going to go into that because we don't really need to know that. But you know, there's a specification for the frame structure that's 3309, 1979, and procedure and whatnot. We don't really care about that. All right. It is a connectionless protocol, which is important as well because it doesn't provide error correction, error detection, unlike other layer 2 encapsulation protocols. It can be used for point to multipoint. Well, it certainly can be used for point to point and point to multipoint connections. All right, meaning that we could actually deploy this in a almost similar to what we would see in kind of a frame relay type of environment. It uses something called a master-slave mode. We don't really need to get into the details of that, but you have a normal response, you have an asynchronous response, but usually it's running something called asynchronous balanced mode. All right. It was originally developed back in the day based on IBM's protocol, SDLC. And using IBM's system network architecture. I don't know if you guys remember some of that stuff back in the day, but it doesn't really specify frame fields. It kind of allows other vendors to utilize the protocol themselves with some customization. That's why Cisco's version of Hdlc is not necessarily compatible with the standard version of Hdlc. So we will talk about that a little bit, but if you're using a Cisco device, like a Cisco router, you want to communicate to a Juniper router, Hdlc is probably not the protocol of choice. All right. Let's see, what else do I want to mention about this protocol? Let's talk about the framing a little bit. Hdlc frames. This is a layer 2 protocol, so we do refer to the framing concepts. Let's just put this here. They can be transmitted over serial lines that are synchronous or asynchronous. There is no mechanism to actually mark the beginning or the ending of a frame like you would see with, say, an Ethernet frame, where you have a preamble and a postamble. But the beginning of each frame does need to be identified. So there is a flag field that's part of the Hdlc frame header, and it's actually a sequence of bits that's actually utilized to identify the frame delimiter. The sequence is very much like Ethernet. It's 8 bits. It starts with a 0 and it ends with a 0, and it has a bunch of 1s in the middle. All right. So let's take a look at how this would look in a Cisco router, and talk about maybe, well, there's really only one command that you need to be able to implement this protocol. Let's go back here. Go into our console. Let's get the other guy here too. All right, so I really don't have anything configured on these devices at all. But if I do a quick show interface serial to 0, you can see even though the interface is presently shut down, the default encapsulation is Hdlc. Configure interface serial 2/0. We'll do a no shut. And I believe on this side, if I'm not mistaken, it's 2.1. Yep, 2.1 on that side. Config T, interface serial 2.1, no shut. All right, so I'm going to put an IP address of 10.0.0.2 on this side. And I will put an address of .1 on the other side. .0.0.1. Now if I do a quick show IP interface brief, we can see the interface is up. We're running Hdlc encapsulation. In fact, if I come back to my WAN circuit and I start a packet capture, you will see that we will have Hdlc frames moving back and forth between the routers. It is the default encapsulation protocol that is used by Cisco routers. And it's a very, very basic layer 2 encapsulation protocol. It really doesn't have any additional features. There's no authentication. There's no multi-link configurations. And we do have some problems with interoperability, but it's actually implemented with just one single command. So we've got Hdlc running between these two routers. Let's see, we might have to generate some traffic because it's a very basic protocol. So let me go ahead and generate some pings here. It's still loading. All right, so I'm going to just do a ping to 10.0.0.2 and hopefully I'll see some of that traffic being captured. Let's go back to our Wireshark. Huh, not seeing any captures. Let's see. Restart the capture. I was hoping to be able to see some of the data going across the link here. Let me try something real quick. I want to make sure that my capture is working. Interface serial 2.0. Shut. No shut. We're not seeing any of the captures here. Let me try this as well. Config T. Oops. Encapsulation PPP. I want to see if I see. Yeah, I had this issue before with capturing data over a serial link. Doesn't seem to work very well. Let's see. Let's go back to our GNS3 here. See if it'll give us an ability to take a look at it in SolarWinds. If not, it's not a big deal. We will see a little bit later on what PPP looks like. We're going to get some debugs with PPP. Let me stop this capture. Yeah, I know. Go away. All right. But let's go back to our command line here. So in the command that we would actually use, you'll notice that my interface has gone down because if I do a show run, interface serial 2.0, I'm no longer running Hdlc encapsulation, I'm running PPP encapsulation. In fact, if I do a show interface serial 20, you can see that right here. Encapsulation is PPP. We've sent a link control protocol request. We'll see about that later on. But obviously I'm not getting anything back because the other side of the link is not running Hdlc. So the only command to actually convert this to Hdlc is encapsulation. And you can see we have lots of different choices here. But we're going to go ahead and implement the Hdlc synchronous mode on this particular interface. That's the only option we have to enable or disable Hdlc. You should see the interface is going to come up. It's going to become operational at the data link layer. If I do a quick show IP interface brief, you can see that the interface is up. All right. So it's a pretty basic configuration. If I do a show run interface serial 20, I can see that that's really the only command that I have. It doesn't show up here because it is the default. This is the IP address on the interface. Now, one of the things that I wanted to show you as far as verifying the transport is the show controllers command serial 20, because the show controllers command will identify whether or not at the physical layer the circuit is up and running. All right, now we're simulating a DCE to DTE connection. We can see the line state is up. It's a V.11 DCE cable, so it's receiving the clock rate of 201.5.232. Now if I go to the other router and I do a show run interface serial 20, you're going to see that I pretty much have, 21, sorry. I pretty much have the same configuration, right? I haven't actually identified a clock rate. And so GNS3 is already kind of simulating that clock rate scenario. Now, usually what would happen is the DCE side of the cable would be providing the clock, and the DTE side would be receiving the clock. So if I do a show controllers, serial 21, you can see that this is being identified as the DCE side as well. So unfortunately with GNS3, it doesn't quite simulate the environment as it normally would. One side would be the DTE, one side would be the DCE, excuse me. Data communication equipment would be the provider side. That would be where the CSU, DSU would be. And then the data terminating equipment would be the customer side. Usually it's the DCE side that's going to end up providing the clock. Now I could inject a clock if I wanted to. It's not really necessary in this case, but if I went into serial 21, I could use the clock rate command and I could specify a clock rate in bits per second based on whatever clocking I wanted to put on there. So let's say we wanted to put a clock rate of 64,000. All right, now if I go back to this router here, show controllers, you can see that even now it's not necessarily receiving a clock. And I'm going to explain why that is. All right, if I go onto this one, if I do a show controller, serial 21, you can see the clock rate has been specified here. If I do I don't think this works in, let me try this in GNS3, show inventory. It did work. So you can see from the show inventory here that I've got a 4T plus module. Now, traditionally with T1s, especially when we were talking about Hdlc originally, you would have an external CSU DSU that would be providing the clock for that particular synchronization on that line. But the 4T plus has a built-in CSU DSU for each port, which is why the clock rate is only local to that particular interface. All right. None of this stuff you would necessarily need to know for either the written exam or the lab exam. All right. Yep. We could do an in-cap on both sides, Tim, but unfortunately it's, PPP is probably going to provide us more information. The issues that we're running into are not significant, Tim. You guys could certainly decide to use viral if you wanted to, but it's not something that I would necessarily be concerned with. This is not something that you would have to know for the lab exam anyway. I'm just kind of pointing out some of the things, all right? And I believe that Firewall would still have similar issues because it uses essentially the same Linux builds that we're using in GNS3 for this purpose, okay? Now, if you have a subscription to Firewall, you can certainly go and check that. But again, I would say it's not really necessarily a huge concern, especially when we get into more of the mainstream stuff, the mainstream protocol stuff that we're going to be talking about. You're not going to see these little quirky things that you're going to typically see with GNS3 in the lab environment. So I wouldn't really concern yourself too much with it, but I really appreciate the offer. All right. I have a feeling that in Firewall you would see similar issues because they're using the same images that we're using. Okay. All right. So it is a very basic protocol. Like I said, Hdlc, Cisco's version of Hdlc is slightly different than everybody else's version of Hdlc. It's actually called Hdlc. It's kind of an extension of Hdlc. It was developed as a bit-oriented synchronous data link layer protocol, as opposed to being able to perform synchronously and asynchronously. It's what we call a proprietary extension of the standard Hdlc. Even though technically CHDLC has been widely distributed and it's actually been implemented on a lot of different vendors' platforms. There is an alternate framing structure to the standard ISO Hdlc framing structure. One of the primary reasons for the creation, the reason that Cisco created CHDLC was to address Hdlc's inability to provide multi-protocol support, which is something that that PPP does. It provides multi-protocol support because it has that capability built into it. So the CHDLC frame contains an actual field for identifying what the network layer protocol is that's being encapsulated inside of Hdlc. All right. So we have an address field, we have a control field, and then we have a protocol code field, which is what makes Cisco Hdlc unique. And then we have our data, and then we have our frame check sequence. So that's what we're dealing with. Is Hdlc limited to half duplex, or is that a limitation of GNS3? This is a synchronous protocol. We're not talking about Ethernet here. We're talking about a serial link, so we have full duplex communication. I know you see here half duplex listed, but it's a full duplex protocol, and it allows synchronous communication. Okay, that's why it's called a synchronous protocol. All right. All right. Let's see, the address field in the CHDLC frame, obviously because in this particular case, in fact, let me go ahead and pull this up here, because you guys probably are not going to follow along if I just describe it to you. So here's my Hdlc frame. All right, you've got this 8-bit address field. All right, now in that field, all you're going to see is either a hex 0F or you're going to see a hex 8F. All right, the hex 0F represents a unicast Hdlc frame, and the 8F represents a broadcast. I was hoping to show you guys this in the Wireshark capture, but that's okay. Represents a broadcast packet. All right. Then there is an 8-bit control field. So this is called the address field. This is the control field. And in this case, this 8 bits here, well, it's never really used. So that's always going to be hex 00. Remember, we're talking about 8 bits, which means 2 hexadecimal characters to represent that particular field. All right. Now, in the case of the next field, this is where we see the difference. It's a 16-bit field or 2-byte field. and it is called the protocol code field. All right, this is what's unique in a Cisco environment, this field right here. If you were looking at a standard Hdlc frame, you would not see this field. All right, you can equate this basically to a type field. A type field in Ethernet is also 2 bytes. So for example, if I'm carrying IPv4, it would be a hex 0x0800 in this field to indicate that we're carrying IPv4. It would be an 86DD if I was carrying IPv6 and so on. So it allows us to identify essentially what kind of information is being carried inside of Hdlc. All right, then we've got our information field, and this is 0 or more bits. Basically, there's really no definition specifically about how large that field can be, but it does have to be built in multiples of 8. And then we've got finally our frame check sequence, which is our 2-byte frame check sequence. So that's our cyclic redundancy check. So this is our payload, and that's our basic header and footer. Really, really simple frame type, very, very basic frame type, not a whole lot going on with it. Okay? All right. Now, we could talk about SLARP and all that other stuff and SLARP keep alives and whatnot, but it's not really that important. And I don't want to spend a whole lot of time talking about a protocol. Essentially, that the extent of what you're going to see is what is it, why is it the default, and maybe what's the difference between a standard Hdlc frame header and a Cisco Hdlc frame header. Now you know that difference, so let's go ahead and Cisco adds a 2-byte protocol identification field that works basically like a type field in 802. Actually in Ethernet 2, because 802.3 does not use a type field in Ethernet 2. So 0x0800 would be IPv4, and 0x86DD would be IPv6. Those are just some examples. Those are common types that we see with Ethernet. So Cisco Hdlc is not compatible with the ISO Hdlc version. All right, just something to keep in mind. Only command to enable or disable Hdlc is interface config-if encapsulation Hdlc. Keeping in mind, of course, that this is going to run CHDLC by default. Okay, it's not going to run. You're not going to be able to run the ISO version of Hdlc on your Cisco routers. Now you may be able to run the Cisco version of Hdlc on on other routers, but you're not going to be able to run the non Cisco version of Hdlc on Cisco routers. Just keep that in mind. Okay. All right. There's no ARP. There's no addressing. The addressing field, as I mentioned here, is basically, is it a broadcast? Is it a unicast? It is protocol independent. At least Cisco's version is protocol independent based on the encapsulation in terms of payload. Basically, you do an IP address on each end of the serial link. You turn the interfaces on, and you're good to go because it is the default encapsulation protocol. Okay. Ppp is significantly different in this case because Ppp negotiates the upper layer protocols. It has an NCP component, it has an LCP component, and when we get into the details of Ppp, we'll talk about those specifics. All right. HDLC is really just meant to be a very, very lightweight encapsulation protocol. It's not supposed to be an advanced encapsulation protocol. Let's see, if you had Juniper, Chris is asking me, if you had a Juniper on one side, it should still work. It depends on whether or not the iOS on the Juniper platform understands the Cisco variant of HDLC. As Tim mentioned, so I would doubt it. It might be more likely for a vendor that's not as major of a competitor to Cisco as Juniper is, but I can't say no, right? It would make kind of sense that Juniper would want to interoperate with Cisco because they'd be more likely to place their devices into an environment, in a mixed environment. So I would have to do a little research to identify what they support specifically. But if they do not support CHDLC, then it's not going to be an option. Okay. So that's pretty much it for HDLC. Pretty basic protocol. So now we're going to focus our attention on what I think is really more important, specifically for the lab environment and the written as well, is Pppoe. All right, actually point-to-point protocol. Ppp is a layer 2 protocol. We're going to do a little bit of background here before we actually kind of move into the variation of the different configurations of Ppp. So we'll create a section in our notes here, point-to-point protocol. Now, as a protocol, there are some things that I want to kind of describe to you guys about the point-to-point protocol. That I think is important to know, and then we'll talk about point-to-point protocol over the Ethernet. All right, because there's a difference between standard Ppp and what you would see over an Ethernet connection. All right, Ppp is considered a data link layer protocol. It operates at layer 2 of the OSI model. Let me keep my notes here. I mean, these are basic concepts, but it is a layer 2 encapsulation protocol. All right. And it's essentially used to, as the name implies, provide a connection between two different nodes. It can connect traffic from switches and bridges. It can also connect to provide things like authentication, encryption, compression techniques, and so on. Ppp is actually designed, unlike HDLC, to work over many physical layer networks. So it can work over a serial cable, which is what we're going to do. It can work over a phone line. It can work over a trunk line, which is like a special type of phone line. It can work over cellular network connections and so on. It can work over fiber, twisted pair Ethernet, all kinds of things. So it is a unique protocol in that it does have the ability to work over many physical layer functions. Ppp was actually widely used originally when we were talking about service providers providing dial-up access to the internet. All right. So there are two kind of major versions of Ppp. We're only going to focus on one in this case. You've got Ppp-OA, which is your over ATM version, which obviously we're not going to spend a whole lot of time with. And you've got your Ppp-OE, which is over your Ethernet. All right. Believe it or not, when we were talking about DSL, digital subscriber lines, it was actually Ppp-OA. We were running ATM over these DSLs, and we were connecting to these DSLAMs to provide an aggregation point or a multiplexing point for those DSL connections. So it is a very common data link layer protocol. It works over synchronous as well as asynchronous. Synchronous means basically you get the same bandwidth in both directions. Asynchronous is you have different upload or download speeds. And it actually was used to replace another protocol called SLIP, the Serial Line Internet Protocol, which was something that was used widely in the old days with X.25. We also had LACB, or LAPB, excuse me, which was the Link Access Protocol Balanced, and so on. All right. So the only requirement for a PPP connection to work was it worked with all kinds of different network layer protocols. Obviously IP, which is what we're going to focus on, Trill, IPX, DECnet, AppleTalk. So because it had the ability to, it had the NCP sublayer, the network control protocol sublayer, it would work with multiple layer 3 protocols. A lot more reliable too, because it offers different checks to make sure that the packets are being transported correctly, and so on. All right. PPP was actually developed after Hdlc. So what they decided to do when they invented PPP was to include all these additional features that were only seen in, at that time anyway, proprietary Datalink protocols. All right. Not that you need to know this, but I read this document before when I was creating additional courseware. RFC 1661, it's an easy one to remember, was the original RFC for PPP. Okay. Now, Ppppoe is RFC 2516. That's our Ppppoe specification. So if you were to go back and do any kind of additional research, that would be the RFC that I would suggest that you take a look at. All right. Basically, it describes how we can transport point-to-point protocol traffic over a Ethernet connection, which could also be used with DSL as well. All right. 2364, which is the ATM RFC, you don't really need to know. I'm not even going to put it down, write it down, because I don't think it's important to know. All right. So as a protocol, there are 3 major components to PPP. Let me go ahead and put this in here. PPP components. Number 1, we have an encapsulation component. So that's our physical layer component, which is encapsulation. And then we have something called the link control protocol, or LCP. All right. So this is what we use to maybe test the link, negotiate settings. We also use this to maybe, well, let's just call it for now for optional features as well. We'll talk about that in a little bit. That involves things like encryption and so on. All right. So that's the second component. And then the third component is something called the Network Control Protocols component. All right. So that's Network Control Protocols, or NCP. And this is pretty much going to be used to negotiate, let me think how I want to say this, negotiate, well, let's just say parameters for layer 3. All right. I'll get into the details of what that means in a little bit. It has to deal with how we handle communication at layer 3, because we can identify specifically the layer 3 protocols that we're using within PPP. So it is a very important concept. Now, one of the things that PPP does provide is what we call automatic self-configuration. So what happens is the LCP, and I'm not going to write this down because I'll just mention it, but I don't think you need to know it for the tests. What happens is LCP is going to initiate and even close out or terminate connections gracefully. Kind of like you would see with like a TCP session, where you are negotiating the parameters of a TCP connection and then closing out that TCP connection as well. LCP gives us the ability to configure the interfaces at each end, like what are the size of the datagrams that we're going to have, what are magic numbers. I'll show you that in a debug a little bit later on, how we can identify the magic numbers, which is kind of like a session ID for the Ppp session. LCP runs on top of Ppp, and it's going to be protocol. In fact, let me put that here because I saw that in a debug the other day. 0xC021. So that would be a 0 there, not a O. All right. Basically it's used to create this connection. Now there are a couple of ways, so if we want to add authentication to this process, there's a couple of different authentication parameters that are also part of the LCP negotiation. Okay, so actually I will add that as well. Optional features like authentication. Okay, and let's put this as protocol hex C021. So when it comes to Ppp, we have authentication mechanisms, and there are multiple ones, but there's actually 4 different authentication methods that you can use with Ppp. But the most common one is CHAP, or the less preferred one is PAP, Challenge Authentication Protocol. That allows us to establish the connection, and then using a challenge response type of method with a hashing process. And then we have the password authentication protocol as well. All right. Now, that's generally not recommended. We'll talk about that in a little bit. All right. I doubt you would see any kind of reference to configuring PAP anytime soon. Now, there are some other ones. Those are the main ones. In fact, I'll put a little asterisk here because that's what we're going to talk about in this lesson when we get into the authentication piece. But we also have something called EAP, Extensible Authentication Protocol, which would require the use of a back-end radius or AAA type of environment. We won't spend any time talking about that. And then we also have the ability, ICE, yeah, exactly, Chris. We could use ICE as the back-end platform. And then we also have the ability to run MSCHAP, right? And other types of authentication. So we're not going to get into that specifically. But basically, we negotiate all these parameters as part of LCP. Now, once LCP has gone through and negotiated all of the different parameters for the communication, then we have to go in and establish our layer 3 configuration. And that's where we're going to see things like, and we'll see this in the debugs, we're going to see things like ICPC or IPCP. Where'd my mouse go? There it is. All right. So once the LCP negotiations take place, we will proceed to layer 3 negotiations. All right, and that's where NCP comes into play in this particular case. So you might see something like IPCP. We'll see that in a little bit. That stands for the Internet Protocol Control Protocol. Kind of a weird name. That's typically for something like IPv4. Or you might see IPXCP. That's for IPX. I'm not even going to write that down because we don't really use that anymore. That was the Novell Transport Layer Protocol. Or you might see something like ATCP, which is AppleTalk. Again, probably won't see that, but might actually see this one, which is IPv6CP, which is IPv6 negotiation. All right. So we'll see that actually when you're doing a show interface, and you can see what protocol is being negotiated. Obviously, for the most part, we're going to see IPCP for the network layer negotiations. All right, but Ppp allows all kinds of network layer protocols to operate on that communication link. In fact, we can even encapsulate multiple protocols on the same link. All right. For every network layer protocol that's actually used on the link, you're going to get a separate NCP that's provided in order to encapsulate that information. I'll demonstrate that as part of our configuration. In fact, let's go ahead and go back to our GNS3 and let's configure some IPv6 on this as well. So let's put in, here 2001 dead beef for dad :1/64. All right. And on the other side, let's put in 2001 dead beef for dad :2/64. So we'll do a point-to-point connection. And I'll show you how we can see that we're actually encapsulating both IPv4 and IPv6 information. Let's go to our router, config T, IPv6 unicast routing to turn on the transport interface or the protocol stack. IPv6 address 2001 : dead beef for dad :1/64. And I'm also going to do another thing here just to make our lives a little bit easier. IPv6 address FE80 :1 link local. I'm just going to set the link local address statically on that side. Otherwise, we're going to be using the EUI64 process. So IPv6 unicast routing, interface serial 21, IPv6 address 2001 dead beef for dad :2/64, and IPv6 address FE80 :2 link local. All right. So if I do a show IPv6 interface brief, you can see, actually we do a show run, show interface serial 21. We're still running Hdlc, right? If I did a show IPv6 interface serial 21, you'd see the same thing, right? We've got our global unicast address. We're participating in the all hosts multicast group and all routers multicast group. We're not necessarily seeing the encapsulation identified here, but we're still using the same encapsulation. In fact, I could ping 2001 : dead beef :for dad :1, and it works just fine. So I'm doing an Hdlc encapsulation, but I wanted to identify what it would look like when we're running PPP, which we're going to switch to here in a little bit. Okay. That's kind of the background of PPP. I'm just trying to think if there's anything else I want to describe before we move on. Oh, the magic number. Absolutely, that's important. We use this magic number to detect loops in our PPP environment. So whenever a node, and we'll see this in a debug a little bit later on, but whenever a node sends a PPP LCP message, the message includes a magic number. Now, if for some reason the line was looped, the node receives an LCP message with its own magic number instead of getting the message, getting a message from its peer with its peer's magic number. So we talked about the magic number. I briefly mentioned it, but that's the purpose of the magic number is for loop detection. All right. Now we did also talk about how we use LCP to identify, all the parameters of the connection, what kind of WAN connection it is, and so on. But let me talk a little bit about what some of those options are, because that's one thing that you will need to know as well. All right, so let me go back up here. Actually, let me just kind of do this at the bottom. So LCP options include the following. Number one, it's going to be authentication. We already kind of mentioned that. We can the peer routers can exchange authentication messages, and we can use PAP as an authentication option, or we can use CHAP as an authentication option. And we'll talk about the specifics of authentication a little bit later on. We can also do compression. All right. So, this is typically a protocol that we're going to be running on a slower speed link. So we may have to have some sort of compression technique to increase the effectiveness of the throughput on the link itself. And then the data would be decompressed at the other side of the link. All right. We also have the function of error detection. So let me put that in here. Error detection. And that's just going to give us the ability to identify any kind of faults that exist. All right. There are two numbers. There's a quality number and there's a magic number that allows us to identify reliability, to provide loop-free data link connections. That, like I said, that magic number helps detect whether or not there's a loop-back condition on the PPP link, and so on. So if we're not using that, by the way, we're going to see that that'll be used in the Cisco environment, but the magic number was basically transmitted as a 0 if it wasn't actually being used as part of the configuration. And we have a separate unique magic number that gets generated randomly on each side of the link. Another LCP option would be multi-link, what we call PPP multi-link. It's kind of like Ether channel for PPP. It allows us to load balance PPP traffic through multiple links in the process. Okay. So let's talk a little bit about the structure of a Ppp frame, because we did talk about the structure of an Hdlc frame. So let's go back to my paint window here. All right, so that was our Hdlc frame. What is this on here? Let's get rid of that. All right, now let's talk about our Ppp frame. Again, not something you would, of course, need to know for the lab. All right, but it's definitely something that could be useful for the written exam. So the very first byte we have is what we call our starter frame delimiter. It's a 1 byte field, and it's written as a 0x7 echo to identify the beginning of our Ethernet frame. I mean, our PPP frame. All right, just like in Ethernet, we have a preamble. Well, we have, in this case, I wanted to rewrite that because it wasn't very legible. All right, now we also have another byte. That's the second byte in the frame. This is called this is the flag field. This is the address field. So unlike Hdlc, where I have unicast and broadcast, in PPP, because it is literally point to point, all I have is one value that goes here, which is a standard broadcast address for PPP, hex FF. Okay. And then we have another field called the control field. That's also 1 byte. That usually is going to be represented by hex 3. We can talk about that a little bit later on. Those values could change depending on the type of PPP data. All right. And then we have a 2 byte field called the protocol field, which is like the type field. Or in Hdlc, it's like the protocol identifier field. It allows us to identify the actual protocol. So I'll just put protocol here, which we know will include what? It'll include like hex 800 or hex 860D or whatever. All right. Then we have our datagram itself. This is our payload. I need to get a skinnier finger. All right, so again, 0 or more bytes in this case. So this is my payload, my actual data, or what we might identify as the datagram. All right, and then we have some padding bits possibly. That would actually be included as part of that field if we have to include any additional padding bits. And then we have our frame check sequence. All right, so we've got the last thing here is our FCS, which again is 2 bytes, just like it is in Hdlc. That's our CRC. And then we have our flag field, 0hex7e, again, to identify the end of, that's a 1-byte field as well, to identify the end of our Ppp fragment, our Ppp frame. If I have successive Ppp frames, I'll basically omit that particular field. All right. Now, as far as the actual payload size, it does have a variable length. It can be negotiated using an MTU value. By default, it is 1,500 bytes, but it could also be padded on transmission if we needed padding bits in there and so on. All right. Ppp frames do get encapsulated in some sort of lower layer protocol that provides us framing. It might also provide information like checksum and so on. So Ppp on serial links is usually going to be encapsulated into a frame like Hdlc. It's kind of an interesting concept. In our case, we're going to be using Ppp as the encapsulation protocol, but we can actually encapsulate Ppp into other protocols. All right, you guys understand what the frame check sequence is used for. That's determine whether or not the frame itself has an error. There's a checksum that's actually computed based on the frame itself. It's a CRC, a cyclic redundancy check. In this case, it's a 2-byte CRC. We don't use a 4-byte CRC in this case. So we're using the polynomial. We don't really need to get into the math of it, but there's a polynomial that we use, x to the power 16 plus x to the power 12 plus x to the power 5 plus 1. And that gets into the whole idea of how we identify whether or not there's an error on the link. Basically, when I describe it, I just say, look, it's a hash that allows us to identify when there's an error based on whether or not the cyclic redundancy check fails or succeeds. Okay? So the last thing I want to talk about before we actually get into the configuration and troubleshooting and verification are the phases of Ppp, because you'll definitely have to know this for the written exam. I doubt you'll probably have to know this too much for the lab unless you're going to get caught up in some sort of weird troubleshooting scenario, but I doubt it. All right. So one would be the link is dead, meaning that that's a complete failure of Ppp. All right. The other is the link establishment phase. And as you can imagine, this is where Lcp is trying to negotiate the status of the link. If the link, if we can establish the link, then we move into, you know, either authentication, if authentication is configured, or we move to the NCP piece, which is the network layer protocol phase. All right, where NCP kind of does its thing. Now, if I do have authentication, let's say the authentication phase is active, which is optional. We don't have to use authentication with Ppp. This allows essentially both sides to negotiate authentication before the connection actually gets established. So again, authentication is part of LCP, it's not part of NCP. All right, and that's where we can do CHAP or PAP authentication. Now I'm going to talk about this in more detail a little bit later on, but remember, well actually I didn't tell you this, so I'm going to tell you this now. We're doing kind of, we can do unidirectional authentication or bidirectional authentication. You do not need to authenticate both sides of the link. And if you remember, this came from the days of dial-up and ISPs. Well, ISPs were not being authenticated by the clients were being authenticated by the ISP. So in a lot of cases where we're using DSL, that authentication only occurred in one direction, if that makes sense. Okay, so we'll take a look at what those authentication methods look like and what the process is for authentication a little bit later on. And we'll actually do some debugs, and I'll show you how that authentication process takes place. Okay? Unidirectional. There we go. All right. So now we move into what we call the network layer protocol phase. Now this is obviously where NCP is going to be involved. So we've gone kind of down, from a down state to our link establishment phase. And this, I should put some spaces here to indicate that that's still part of that link establishment phase. And then we move into our network control phase, which is really phase 2. All right. So this is where we identify the control protocols, the network control protocols. For example, IPCP for IP services over IPv4, and so on. Get negotiated. The data transport for all the protocols will get started here, right? Closing down of network protocols will occur at this phase as well. But basically, this is where we're negotiating our layer 3 transport. And then the final phase would be the link termination phase. And this is where we're closing down the session, right? Again, that would be not something we would see too much today, but you would see this maybe in the dial-up days when we were using PPP as our transport, okay? This could also happen with the termination. We could jump to termination if authentication fails, for example. If we get a bunch of checksum errors on the path, we could see the termination phase and so on. All right. Now, one other thing I want to mention, which you guys do need to know about, is something called Mlpp. Some people refer to it as just MPPP or MLP. I'll put these on here, but on the test you're going to see it as Cisco uses Mlpp, which stands for multi-link PPP. All right. So what this does, oops, I wanted to move that down a little bit, is this allows us to effectively join, sorry, I was sneezing between those words, join multiple serial links together for aggregate bandwidth and redundancy. Now, you won't have to configure this on the test. You're just going to have to be kind of aware of what it does and what it's for. All right, and that's what we're, kind of why I'm mentioning it here. It's obviously part of the process. It doesn't necessarily have to be used on a physical serial link. You could do this with like multiple modems. If you had 2 analog lines and you wanted to join 2 analog lines together to give you additional bandwidth. All right. So it's just another form of link aggregation, if you will. All right. And it's been supported on Cisco iOS forever. I think 11 something or maybe even 10 something. All right. So the only thing that this provides that doesn't exist with a single link connection is the PPP frames could arrive out of order. The frames could be divided up across different physical connections. So multi-link PPP numbers the fragments so that they can be put back together in the correct order when they arrive at the other side of the link. Okay. All right. Trying to think if there's anything else I really want to talk about. We also have tunneling mechanisms, of course. I'm not going to really get into the details of the tunneling options. We've got point-to-point tunneling protocol. Basically, that's just a form of PPP when you have 2 hosts using GRE encapsulation, and they're using compression techniques as well. Okay, you could add things like SSL or SSH or L2TP to create different network interfaces and so on. And you could also use some you could use some IPsec on that to provide encryption as well. All right. So that's kind of our background of PPP in general. Now let's go ahead and take a look at some of the details. All right. The first thing that we need to understand is that there's only really one command that's necessary. Let me do configuration of basic PPP. On the interface, config-if, we're basically just going to run encapsulation PPP. All right. So if I come into my device here and I go into interface serial 21, I type encapsulation PPP. I'll come to the other side, encapsulation PPP, show IP interface brief. We can see that the interface is up and up. And if I do show interface serial 20, we can see that we're actually using encapsulation PPP. LCP is open, which means we're not running any authentication. And we're actually running 3 different transports. Oh, I didn't mention the CDP CP1 as well. So we got IPCP for IPv4, IPv6 CP for IPv6, and CDP CP for Cisco Discovery Protocol. Now I should be able to, in this case, hopefully see, it could just be an issue with Wireshark capturing communication across a serial link, but let's see if it works with PPP. All right. I think this is more of an issue with how Wireshark integrates with GNS3 as opposed to a GNS3 issue natively, but we'll give it a shot. See if we can capture some of that data. Yeah. So that's unfortunate. We're not going to see the captures on the serial link for some reason, but that's okay. Again, I think it's just a limitation of doing serial to serial connections. I'll see if that's just a bug. Maybe there's something that I have to configure in addition to something I have to tweak on GNS3 to make it work. All right, but that's okay. We can use debugs to see a lot of the information that I want to show you anyway. All right, and that's what we're going to do as part of the process. All right, let's see. So we see IPCP. Let me go back to my command line here. We see IPCP, which is, of course, the IP control protocol for IPv4 over PPP. We see IPv6 CP, which is the IPv6 control protocol over PPP. And we see CDP CP, which is Cisco Discovery Protocol over PPP. As I mentioned in our theory section, PPP uses the link control protocol to negotiate what higher layer protocols are going to be used or are going to be encapsulated. So in this case, because we're running IPv6 on the interface and because we're running IPv4, and it's interesting that CDP would be kind of identified here. I suppose that makes sense because we're running, if I do a show CDP neighbors, I should see, yeah, CDP information for my neighbor. That's all going to be encapsulated inside of PPP. All right. So PPP is actually used to negotiate addressing assignments and routing information. Let's do our first debug so I can kind of identify what it is that we're actually looking at. All right. So I'm going to do a debug in this case. Ppp Negotiation. All right. What we're going to see is that we're going to, I'll shut down the link and bring it back up in a second, but we're going to see how the session is being negotiated. All right, so let me go into interface serial 20 and shut it down. Wait a second for the interface to go down. So we can see that we see some events of closing down the session, but let's take a look at when it comes up first. So we'll do a no shut. And what you're going to see in this particular case is essentially the negotiation of the Ppp session. Okay, so let me do an undebug all real quick and scroll up, and we'll take a look at what's happening in this process. All right, so the link state changed to up. we're sending a state up notification, and then we're processing, the state up. So now we're establishing the Ppp session. All right. This is a dedicated circuit. We don't really care about these IDs or whatnot, but this is essentially the part that's important here. You can see that I'm sending a configuration request message out the link, identifying what my magic number is for my session. Okay? So I'm saying, okay, the session is starting. I've sent a request. Again, another configuration request. Another configuration request, and you can see in this case the magic number is has changed in this process. I think this is a part of the interface coming up, right? We had a timeout, and so we sent another configuration request. So this is actually where we actually got the response from the other side. Right? You see the conf ACK indicating that we've acknowledged the configuration request to the other side. All right. So we're negotiating essentially the different phases. You can tell that these are messages that are sent by myself, given a magic number here, and this is the information that I'm receiving. Received conf ACK. So this is the magic number that the other side is using. This is the magic number that I'm using, and so on. All right. So this is all part of that LCP phase. And notice that once that occurred, the link layer 2 came up. So that's where we, when you do a show IP interface brief, you see the protocol and the status indicating the physical layer and the protocol indicating the data link layer. It was only after we went through all of these negotiations of magic numbers and identifying whether or not we're doing any kind of authentication. State is open means we're not doing any authentication. So we've established the LCP function. Notice these are all LCP messages here. Now we see that LCP is up. Now we're going to go through and negotiate all of our NCP components. So IPCP is going to be negotiated. IPv6 CP is going to be negotiated, and CDP PC is going to get negotiated. All right. You can also see that I'm actually identifying my address. Actually, this is the other side sending me a conf request, identifying their address. You should see a message in here, right here, where I'm identifying my address as well. So I'm actually identifying the addressing information that is configured on both ends of the link itself. Now we'll talk about what this looks like when we start to add authentication to this process as well. But I want to show you something else that happens with this PPP process. If I do a show IP route, you will notice that that the router, this is the left router, inserts a host route for the other side of the link. Remember, this is a data link layer protocol. It's not a network layer protocol. So I could actually come into this router here and do an IP address of 1.2.3.4, 255.255.255.255. Oops, try 252 on, well, let's just do a 0 in this case, okay? And I could actually, we would see the renegotiation take place here, show IP route, and you can actually see that it inserts a route for that destination. So I can actually ping 1.2.3.4, even though they're not on a common subnet on that serial link, because PPP is not a network layer protocol. It's a data link layer protocol. So it's actually inserting these directly connected host routes based on that concept, that it's a network layer, I mean a data link layer protocol. All right, it's kind of an interesting thing. You would look at that maybe in a configuration of the lab and go, wait a minute, that's not right. These guys need to be in a common subnet, but actually they don't, because we're negotiating the layer 3 process. If I would have had the debug running, I would have seen in that debug process the host identifying itself as 1, 2, 3, 4 for the IPCP component. All right. So if I do a debug Ppp negotiation, I can see that information. We'll go ahead and take a look at that when we go in to do our authentication piece as well. All right. Now, as far as the configuration goes, that's pretty straightforward, right? We turn on the encapsulation. If I do a quick show run, interface serial 20, you can see I've only got just one command related to PPP, and that's encapsulation PPP. All right. Now, let's see, we wanted to add authentication to this process. As I mentioned before, we're going to talk about PAP and we're going to talk about CHAP as our authentication options between the two devices. We'll start with authentication PAP, which stands for the Password Authentication Protocol. It's authentication that occurs in the clear text, in clear. It's not encrypted, and for that reason, it's not generally recommended, right? The blueprint, the CCIE blueprint, is only going to require you to understand the difference between PAP and CHAP. You're not going to have to know MS-CHAP or EAP, which are the other two options that we have for authentication. Okay. If you remember Pppoe, which is essentially what we're going to, well, actually, we're not going to configure that in this case. We're running basically PPP, straight PPP, but we could actually run PPP over Ethernet with CHAP authentication, or we can tunnel DSL and ATM communications over a link to provide for communication over a DSL connection. All right. So in the case of PPP authentication PAP, we send two different messages back and forth. Number one, we send an authentication request, which is what we refer to as the challenge process of the authentication. And then we send the receiving client, which could be the router 2 in this case, is going to send an authentication response. All right. In this case, we're identifying essentially the authenticator and the authenticatee. So let's say router 1 on the left is the authenticator, and the router 2 on the right is the authenticatee. All right. Now, we could configure, say, for example, PPP PAP refuse if we want to refuse PAP authentication, or we can set the username and so on. All right. So let's go ahead and go through the process. Let's say, for example, I want R1 to authenticate R2. So the first thing I'm going to do is I'm going to go into the interface, and I'm going to specify the authentication method that we're going to be using. Okay, so that's going to be Ppp Authentication. Oops. And you can see here that we have several different options. I can use CHAP, I can use EAP, I can use MS-CHAP or MS-CHAP v2, or I can use PAP. Like I said, the extent of what you're going to have to know on the exam is PAP and CHAP. So let's say we're going to go ahead and enable PAP authentication. You'll notice as soon as I did that, the line protocol went down, meaning that our LCP negotiation has now failed. If I do a show interface serial 20, show IP interface brief, I can see that the layer 2 status is down. If I do a show IPv6 interface brief, we would see essentially the same thing, up, down. So again, because this is a layer 2 protocol, it applies to both protocol stacks. All right. Now let me run a debug PPP authentication, so we can see anything that's that might be happening with this process. Let's actually do a shut on the interface and a no shut to see if we can see any kind of messages coming across indicating that authentication is required. Let me see. I may have to run it on the other side as well. Let's do a debug Ppp negotiation as well, just if we can see what's happening in this case. All right. All right. Let's do it on debug all because it's gonna. you can already see the messages here indicating that Ppp authentication is supposed to be used, right? As soon as that stops capturing that debug, should have done that right away. All right, so we're seeing the termination. This is inbound. I stands for inbound, O stands for outbound. So this is an outbound configuration request. This is an inbound configuration reject. And we're saying, okay, we're rejecting the communication because the authentication protocol is Ppp, but I'm not running Ppp on both sides of the link. All right. So we see, like, for example, where it is, O configuration request right here. This is an example of saying, okay, this is my magic number. This is outbound, so I know that this is coming from router 1. This is my configuration, my magic number, and I'm saying that you need to be doing Ppp authentication. In the conf ACK, the inbound conf ACK, let me see if I can find one. I might have to scroll up here. Let me go up to kind of the beginning here. So here's the configuration request. All right. You'll notice here that this is an inbound configuration request. This is outbound. You can tell what's missing here is the authentication piece. You'll notice that the magic numbers are unique, which makes sense because one side's going to use one magic number, the other side's going to use a different magic number. So we can see that obviously this is just going to continue to cycle through because one side of the link is running password authentication protocol and the other side is not. So if I come into this router now and I do Ppp Authentication, Ppp, so now we're both matching. Let me go ahead and do my debugs here. Ppp Negotiation and Ppp Authentication. Do debug Ppp Authentication. All right, I'm just going to wait to capture a little bit here. And I'm going to do an undebug all. All right, wait for that to kind of calm down a little bit here. You'll notice that we're still obviously the link status is still going to be down because we're requiring password authentication, but we haven't actually identified password authentication. All right, so if I scroll back up here and I take a look at, still kind of going through the process. Let me make sure I turn that off. Undebug all. All right, now we can see that the inbound and outbound requests actually match, right? Here's a configuration request with Ppp, magic number, all right? And for the outbound request, right here, there's inbound, there's outbound, Ppp, magic number, all right? So everything looks good, but of course we haven't identified a way to authenticate one another, or at least even one person authenticating the other person, all right? So we can see that the configuration is being rejected in our status. I'm trying to see if I could see yeah, right here. LCP failed to negotiate because we didn't have any way of authenticating. All right. So there's all kinds of debugs that you might configure, but these are the two most common ones. Debug Ppp Negotiation is probably the most common, and Debug Ppp Authentication. Now, we're not even getting to the authentication phase because we don't have the right parameters, so we're not really seeing much from that debug. All right. So, again, as I said, we kind of create these host routes that get installed on either side of the link to identify. This was used primarily for like dial-on-demand. And what you would typically do is if you wanted to be able to reach those destinations over PPP, you would redistribute those host routes into your IGP. And the route just simply gets added as a directly connected route. It doesn't matter really what the other side of the PPP link is configured at. All right, so let's go ahead. I'm going to clean this up a little bit. Config T interface serial 2.1. No Ppp authentication, Ppp. And we're going to, so I've basically got this guy using its basic configuration, interface serial 2.1. just regular encapsulation of PPP. So I'm going to configure this so that router 1 is going to send the challenge, and then router 2 is going to respond to that challenge. All right. I already showed you guys how the configuration is rejected based on one side. We never get to the IPCP phase or the IPv6 CP phase or CDP-CP phase, and the interface is down. All right. And that's because I have, if I do a show run interface serial 20 on this side, I have Ppp Authentication configured on this side, but the other side is not configured to respond. All right. Now there's a couple ways that you can do this. Probably the most common way, well, you could do it globally or you could do it on the interface. But the most common way would be to go ahead and configure authentication directly on the interface. So I would go in interface serial 21 and I would say Ppp Ppp sent username. I'll just call it R2 in this case, and the password will be CCIE. All right. Now if I go back to my router over here and I do a debug Ppp Negotiation, all right, now we're going to actually see some additional messages. Let's do an undebug all. Normally I wouldn't recommend running this in the console because it's very chatty. But if I do an undebug all, you can see that, well, several times here, we're getting authentications failed, right? So we are actually receiving a config. We go through the authentication process. We're authenticating R2. So we're getting that username from the router. Authenticating, and we're getting a message, authentication failed, user failed Ppp authentication. Now we're terminating the connection. All right. So if you kind of look at this, how this is supposed to look, from the process of authentication, you've got R1 on the left. It's got this serial link to R2 on the right. And what's happening in this case is R1 is sending a Ppp request to R2 indicating, hey, I want you to authenticate. And then the user is going to send its, or the R2 is going to send its username, and it's going to send its password, which in this case is CCIE. All right. Now, normally what I should see is I should see an acknowledgement saying, okay, you're now authenticated, and PPP establishment, we can move into the NCP phase. All right. Ppp and CHAP are a one-way process. You could decide to configure it in both directions, or you could simply authenticate the client or the server. All right. Now, naturally, in the case of dial-up in those days, we were simply authenticating the client. We weren't authenticating the server. All right. So something to consider as part of the process. All right. Sorry about that. All right. Now, obviously, the authentication request is being sent because we have Ppp Authentication Ppp, but obviously there's no way for router 1 to verify router 2. All right. So what we would actually do is we would use a local database to verify router 2. Exit, username, R2. Now we can use the secret option as well, CCIE. Now if I do a debug Ppp Negotiation and debug, we should see the authentication is still failing. Why is that? Oops. I wonder if because I use the secret option. Let's try this. Interface serial 20 Ppp authentication. No, let me do Ppp. Actually, let's do this. Well, okay, so because I'm using a username, in this particular case, I would probably have to go ahead and authenticate using AAA. Remember, the username on the left router, R1, wasn't configured in global configuration mode. So even though I've added the username, I haven't really specified a way for Ppp to authenticate. So I still have to specify a way for Ppp to authenticate. So I'm going to do a AAA new model, and I'm going to do a AAA authentication. And you'll notice that, oops, let's try that again. AAA authentication. You'll notice that one of the options I have is to set the authentication method for Ppp. So I'm going to do Ppp default local. So that says, okay, let's go ahead and use the local username database to authenticate Ppp. So now if I do a show IP interface brief, I should eventually see the protocol come up. Let me try one more thing. No username R2, username R2, password CCIE. Yeah, I'm wondering if because I was using the secret option, because we're using one-way authentication with PAP, whether the secret option caused it to fail. Let me go ahead and experiment with that real quick. So no username, because we can see that the status changed to up based on the authentication. So no username R2. We should see the Ppp, the link go down to show IP interface brief. And actually, we would have to wait for a timeout period, because remember, authentication only occurs one time, and then that link maintains its establishment for a period of time. We're not constantly doing the authentication. So let's go into interface serial 20, do a shut and a no shut, and show run or show IP interface brief. Let's try that again. I probably did it too quickly. Shut. Wait for it to go down. There we go. No shut. Now it's going to go through the negotiation process again. It should fail because I got rid of the username. Did I get rid of the username? Show run pipe include username. Why is it authenticating now? That's strange. Show run interface serial 20. We're still running Ppp Authentication. It's weird. Oh, that's weird. So it was reporting that it came up. The state changed to up. Ah, never mind. That's physical layer, right? Of course, the state is going to change to up, but the protocol is down, which is what we would expect because we're not doing any authentication, or we don't have a way of authenticating the other side of the link. So I'm going to type in username again, R2. The username is what we specified in the configuration of the interface here. Now, if I didn't do this, Ppp sent username, what I would have to do is I would have to create, set up AAA on this side and do mutual authentication, and each router would have the username of the other router's hostname with a common password. They'd have to have a shared password. I'll demonstrate that when we do our CHAP authentication. All right. I'm just trying to see if secret is causing an issue here with the negotiation. Yeah, it shouldn't. I didn't think it would. For some reason it didn't come up before. Maybe I mistyped something or something like that. But anyway, you obviously want to use secret as an option because the passwords are going to be encrypted and not well, in any case, in this case, the passwords are going to be sent in plain text anyway. If we were to do a Wireshark capture, we would see the username and password sent in plain text. So R1 is sending over the PAP request. R2 is responding with its username and password, and in this particular case, R1 is now sending a final acknowledgement indicating that the authentication process was completed. All right, this is a one-way process, and And so we do expect to get an authentication request and an authentication response. Now let's say that we decide to move to CHAP. CHAP is a challenge response type of authentication, where we do not send the username and the password over the link in plain text. In fact, we don't even send the username and password at all. So I just want to confirm, if I do a quick show run interface serial 2.1, we're not doing any type of authentication on this side of the link. We're identifying the authentication that we're using. This is the username that we're sending and the password we're sending. This is the encapsulation, but this router is not authenticating router 1. So I'm going to get rid of this line here. All right. And I'm going to show run interface serial 2.0. I'm going to get rid of the Ppp authentication. And let's take out Ppp Authentication Ppp. All right. So the link should come back up because now we're running just standard authentication. All right. So if I do a quick show run, pipe include user, you can see that we have the username configured on this side of the link, R2, the secret. This is a hashed version of the password. Incidentally, guys, I don't know if you were aware of this or not. This $1 indicates that it's an MD5 hash. This is the actual hash. This is the salt. All the hashes in Cisco are salted, and 80KY is the salt in this particular case. So what you see between the two strings there indicates the salt value that's used. That's to prevent dictionary attacks using rainbow tables. Basically, it effectively makes rainbow tables useless. So you have to go through all the iterations of trying to reverse the password or trying to verify the password. Anyway, not related to PPP. All right, so we're going to do a CHAP authentication. And again, I'm going to, there's a couple ways we can configure this. I'll show you the first way, which of course is to do Ppp Authentication CHAP. All right. And on this side, I can do Ppp CHAP, and I can specify the host name, the password. I'm not going to use an alternate host name because I'm just going to send the host name that was configured on the device. So I can just simply say password, and then I can specify my password if I want the encrypted version or the non-encrypted version. So we'll do CCIE again, and we should see the link come up. Show interface serial 2.0. Yeah, so the line is up, protocol is up. Encapsulation is PPP. That's strange. Show run interface serial 2.0. Ppp Authentication CHAP. Yeah. I'm wondering why it's saying LCP open in this case. Let me do a debug Ppp Negotiation. Sorry, debug Ppp Negotiation. And let's go into interface serial 2.0, do a shut. And a no shut. Undebug all. So I should see, as part of the negotiation process, I might have did it too quickly. Let's try that again. Do debug authentication and negotiation. And no shut. All right, let's wait for it to come up. So what we should see is now that we're forcing CHAP authentication. All right, interesting. I get an authentication failed. All right, let's do an undebug all and see what we see here. So I'm getting an authentication failed. Let's try this again. So here's our outbound challenge. So let me explain what's happening in this particular case. Okay. login failed, authentication failed, user failed, chap authentication. I'll have to find out why that's happening. But essentially what's happening in this particular case is R1 is sending a challenge. Okay. Excuse me, I had to sneeze again. R1 is sending a challenge. So rather than sending the password, R1 is hashing a value and sending it over to R2 saying, hey, I need you to authenticate by verifying this particular hash. Okay, so R2 is sending a response to that challenge by essentially generating the hash. Actually, the challenge that comes from R1 is a message, open message, and then the R2 is supposed to hash that message with its password. And then R1 would verify whether or not the authentication failed or was accepted based on that hash. All right, so it looks like we're failing in this particular case. We're terminating the session. And the question is, why are we failing in this case? All right, so the left router is configured for Ppp Authentication chap. We get kind of the same errors, but in this case we're negotiating chap instead of Ppp. All right, the right router agrees, but again, doesn't really have anything to authenticate with. Actually, it should in this particular case because we did add the authentication properties. We can see the challenge coming in. If I were to come into this router and do a debug Ppp Authentication, I should see the challenges coming in. Let me do a interface serial 20 shut. No shut. I should see the I see the challenges coming in. All right, let me do an undebug all. So I can see that the challenges are coming into this router here. All right, inbound challenge from R1. Sent authentication request, received a sent authentication failed, using hostname from the configured hostname, using the password from the interface chat. So it's kind of strange that it's actually failing because I am using the hostname and I'm using the password that's configured on the interface. So if I do a quick show run interface serial 21, I can see that the password, Ppp chat password, is CCIE. That's the unencrypted version. And the host name is R2. So I'm going to do one more thing here. Config T, no username, R2. Username, R2, password, CCIE. Yep. So the state changed to up. Show IP interface brief. Yeah, that's really strange. It should have authenticated. This could be a bug in GNS3, possibly. I've seen this before in the real world as well, where using the secret option initially, for some reason, doesn't work on a username. I don't know if it has something to do with the protocol or whatnot, but it should have authenticated because I have all the appropriate configurations. I didn't identify a non-default username on the interface. I'm using this password. In this case, I was able to authenticate. So if I do a show IP interface brief, I can see that the interface is up. I can ping 1, 2, 3, 4. No problem. All right. So that should have been the extent of the configuration that I had to have. Show run pipe include username, which in this case, I went ahead and used the unencrypted version. Let me try this again. Interface serial 20. Shut. No username R2. And username R2 secret CCIE. And config T interface serial 20. No shut. See if that comes back up. All right. It should work. Show IP interface brief. Yep, but it's not working. So there may be a quirk with using a secret password versus non-secret. We don't have the option to use the secret option on the other side, but I could show you how we could fix this problem. Okay, and this is how we can fix this problem. Remember I said there's two ways that you can essentially authenticate CHAP users. So if I do a show run interface serial 21, I've specified the PPP chat password on the interface here. So I'm going to come in here and go to interface serial 21, and I am going to do no PPP chat password, and I'm going to specify Ppp Authentication CHAP. Now, this is essentially what you would do. This is what you would do in most cases for a point-to-point serial link in a production environment. You would do mutual authentication. You would authenticate the router on the left, you'd authenticate the router on the right. So I'm going to go into global mode, and I'm going to specify a username of R1 with a secret of CCIE. I've already done this on the other side of the link, a username of R2 with a secret password of CCIE. And what I should see, let me go ahead and shut it down again. Is I should see that the authentication should work in this case. Show run interface serial 20. All right, we've got PPP Authentication CHAP. Show run pipe include username. And as long as I have the other side's host name and they share a common password, they should be able to authenticate. Show IP interface brief. Yeah, it's really strange. It's not working. It'll work, of course, if I go ahead and use a non-secure password. So config T, no username, R2, username R2, password CCIE. Let's do the same thing on this side. Config T, no username, R1, username R1, password CCIE. As long as you have the other router's host name and you share a common password, there should be no issues in authenticating. Show run, show IP interface brief. Yeah, for some reason it came up. I'll have to research that and see what if that's an issue with GNS3, which it most likely is, or if it's something with CHAP authentication where we can't use the secret. I've used secret many times before though. So now in this case, we've got essentially bidirectional authentication. The router on the right is sending a challenge. The router on the left is sending a challenge. We're hashing that challenge and we're sending it back. And then we verify that hash based on the fact that we have a common password and the username. All right, so let me draw a diagram that kind of describes what this looks like. All right. So again, we've got router 1 on the left. We got router 2 on the right. They're connected with this serial link. And what's going to happen in this case is R1 is going to send, let me see. For the secret command, I can't remember, do you need to put the clear text password or 0 and then the clear text password? No, you do not. The 0 is there to indicate, well, if you want to copy and paste that command, you would put the 0, but it just means that the text following is not the encrypted version of the password. Okay. So in this particular case, R1 is going to send a username of R1. So we have a username of R1. And then it's going to send a CHAP challenge. All right. And what R3 is going to do is it's going to take that information. It's going to take the R1 and it's going to take the password that it has configured and it's going to respond with the user of R3, well, R2 in this case. and the password is the hashed version of the challenge, which is an MD5 hash. All right. Sorry, that's not easy to read. That's supposed to say password. Okay. R1 is then going to take that information and it's going to verify the hash. If the MD5 hash that it generates matches the MD5 hash that was sent, then it finally sends the acknowledgement back indicating that the authentication process took place. Okay. So on the right router, we have the username of the left router. On the left router, we have the username of the right router, and then they share a common password. All right. Now you can configure it on the interface like I did originally, or you can have different authentication for different users. So for example, let's say in my topology here, I had another router and maybe R3 that was connected to a different serial interface on R2. I can have different usernames to indicate that authentication. If I configure on serial 2.1, for example, Ppp chap password on the interface, this would apply to all of this would apply to all of the neighbors that I'm trying to establish a session with, as opposed to on a per individual neighbor basis. When you're using the username, then you're obviously specifying the authentication properties that you're using for that particular peer. This is generally recommended because you probably don't want to use the same password for every single peer that you're connecting to. Does that make sense? It's certainly more practical if you're just authenticating one side to go ahead and set the password on the interface. But if you're trying to do mutual authentication, it's more appropriate to go ahead and authenticate on both sides of the link, right? On a per peer basis. All right, does that make sense? Now, I don't know that we'll get into. Maybe we'll get into. Maybe I'll decide. I'll decide whether or not I'm going to do this later on, where we actually are talking about PPP over Ethernet. In this case, when we're just talking about straight PPP, which is essentially what you would have to know for the exam. All right, for the written exam and the lab exam. But I do believe that there's some PPPoE on the written exam. So if time permits, I'll go ahead and add another lesson to where we talk about PPP over Ethernet. But that essentially concludes what we wanted to talk about today. It's pretty basic stuff, not really that complicated. Do you guys have any questions or any comments? All right. So I'm going to end this recording, and then we're going to wrap up our discussion by talking about what it is that we're going to be doing next. All right.